Right, so today we're going to look at section 11.3, which is on the binomial theorem. There's all kinds of uses for the binomial theorem. One of the uses we're going to see is basically how to expand a binomial. That's what we're going to use it for. You can also use the binomial theorem to do some probability. We'll come back to it next week and use it for that too. All right, so what I've done is I just FOILed out a plus b times a plus b. So that would be a squared plus ab plus another ab. So you have 2ab plus b squared. Okay, that's not too bad. But when we start to cube it, okay, let's do that one out by hand. Okay, so we're going to take a plus b times a plus b times a plus b. This will be the last one we do out by hand. Well, I already know what a plus b times a plus b is. I just did that in the last step. And then times a plus b. All right, now the next part, we have to FOIL a plus b times everything we have here. So we're going to multiply a times everything, and then b times everything. Okay, it's not too bad, but it's a little time consuming. Okay, so we get a cubed plus 2a squared, b. Let's see, plus ab squared. Okay, that's the first part. Now the next part, we're going to get a squared b. Okay, and we'll look for any like terms if we can combine them. We're going to get 2ab squared. And last part, b cubed. Anybody see any like terms there? I think there's at least a couple. It's kind of hard because there's all a's and b's and they're all almost the same. Yep.
A squared b and 2a squared b.
Yep, we can combine that together. So we get a cubed plus 3a squared b. Okay, any other like terms?
2ab squared and ab squared.
Yep, these are also like terms. So again, we'll get 3 ab squared plus b cubed. Okay, so that's what you get if you do a plus b cubed. And now if you wanted to do a plus b to the fourth, it gets even worse. So I'm just going to show you what the answer is. And I just want to start looking for patterns. So I did it one more time. Okay, so you could see some patterns. It's not hard to do, it's very time consuming. Okay, does anybody notice any patterns at all? Maybe the last one is a good one to look at because it's the largest one. You can see more of what's happening in it. Does anybody notice anything happening in that? Andrew?
The numbers in front of the variables, I'm blanking on what the word is, they're multiples of the, they're like increasing with the exponents, and then so are the exponents within the actual equation.
All right, let's go back to kind of the first thing you said. Forget about the exponents for now. There's a pattern there too. But how about the numbers in front of, you're talking about like the coefficients of all the terms?
That's yeah.
What? Okay, there is a pattern to those coefficients. That's actually the hardest pattern, I think, for people to find. But does anybody recognize the numbers there? So you have 1, 5, 10, 10, 5, 1. And then above it, 1, 4, 6, 4, 1. 1, 3, 3, 3, 1. 1, 2, 1. Yep.
It's the numbers on Pascal's triangle.
Yeah. These numbers, these coefficients, are the rows of Pascal's triangle. If you were to make that triangle, I'll just go up to there. If you look at that row, 1, 4, 6, 4, 1, Look at these coefficients, 1, 4, 6, 4, 1. So there is a pattern with the coefficients. We can get them from Pascal's triangle. How about the exponents? What happens to the exponents on A as we go down term by term? Yeah?
They increase by 1
On which letter?
on A.
All right, so what does it start out as? It starts out as A to the...
Let's just talking about the first.
Yeah, let's look at that one.
Just talking about from left to right. Oh. So it descends by 1 and then starts increasing.
All right, so the exponent on A is going down by 1 each time. 5, 4, 3, 2, 1. So finally the last term is really A to the 0, but anything to the 0 power is 1. How about the B's?
It increases by 1 going down?
The first one is like B to the 0, then B to the first, B to the second, B to the third, and so on. So the exponents on B are going up by 1. What else? What do you notice if you add the exponents? All the exponents on each term individually. I mean, there's only 2 exponents per term. You want to see a pattern there?
They're all
Yeah.
which is what you raise the expression to.
If you look at what your exponents add up to, they add up to the exponent that you were raising your binomial to. Okay. Also, if you just look at the number of terms, if you raise something to the 5th power, you're going to get 6 terms. If you raise it to the 3rd power, you're going to get 4 terms. Okay, and so on. Okay, so that happens. Everything else I think we figured out. The sum of the exponents is the power you're raising it to. The degree of A is going down by 1, and the degree of B is going up by 1. And lastly, the coefficients, where are they coming from? That was Pascal's triangle. Okay, so with all those patterns, we really don't need to FOIL something like this out. We can use those patterns to figure it out for us. The only thing we might have trouble figuring out is Pascal's triangle. Because if you raise something to a high enough power, you might not have that row in the triangle. Okay, if it's low enough, like maybe even to the 6th or 7th row, we could do that. But eventually, if I said raise this to like the 300th power, even all these patterns, especially this last part, we're going to have to come up with a better way than Pascal's triangle. But for now, we can use that. Okay, so there's Pascal's triangle. That was showing you the pattern. Okay, we've already looked at Pascal's triangle a little bit earlier in the week. The important thing you have to do with Pascal's triangle is start at row 0. Okay, it's going to just make more sense. So if you want to raise something to the 4th power, you're going to go to row 4. Okay? But that assumes you're starting as the first row as row 0. Okay? So if we want to cube something, we'd use the numbers 1, 3, 3, 1. 5th power, 1, 5, 10, 10, 5, 1. Okay? Just make sure your first row is row 0. If you don't start with row 0, then it's going to throw everything off 1 and messes us up. Okay, in Pascal's triangle, each row begins and ends with a 1. And then every entry in the triangle is the sum of the 2 above it. So 4 and 6 gives me 10, 6 and 4 gives me 10, 4 and 1 gives me 5, and so on. And the numbers in the nth row are going to be the coefficients of the expression a plus b to the n. Okay, so we're only using Pascal's triangle to FOIL out binomials. Okay. Could you use it for trinomials? It's a little different. Like if you had a plus b plus c to the n. There's definitely a pattern to doing that. But it's not quite as simple as Pascal's triangle. Okay, we could start to kind of talk about Pascal's triangle as a pyramid. Maybe think of it in 3D. And we could work with some more sophisticated stuff. But for us, we're just going to stick with binomials. Something plus something, or you could also do something minus something. When you have a minus, we just got to be careful with negatives. Okay? we'll try one. All right, so let's try this one. Let's try to do a plus b to the sixth without doing all the distributive property. All right, so what we're going to need is the sixth row, which we have right there. Okay, Brandon, what's the coefficient of my first term using that sixth row? Yep, it's going to be a 1. Okay. And what's going to come after it? 1, and it'll be a to what power?
The 6.
A to the sixth. Okay, what about b? Do we see b in the first term at all? No, it's like b to the 0. It's not there yet. Okay, so that's your first term. Okay, what's my coefficient, Michael, for the second term?
6.
6. Okay, so we're going to have 6. What's going to happen to my power on a? Yep,
It's going to go down by 1.
it's going to go down by 1. Okay, anything else?
And then B is going to go up by 1.
And then b, instead of b to the 0, now we've got b to the first. Okay, and we're just going to keep going until we write out the whole expression. So the next one is going to be a 15. Now it's going to be a to the fourth, b squared. Okay, the next one's going to be 20. A cubed, b cubed. Okay, now the coefficients are going to start going back down. Okay, notice in the triangle they're always symmetrical. Okay, they start to repeat once you get past that middle point to the ones you had before it. So now we're going to go back to 15. A squared, b to the fourth. 6. AB to the fifth. And then my last term is 1 b to the sixth. Technically, you don't need to write the 1 if you don't want to, but just to show you where it comes from. Okay, it's a lot faster than trying to distribute that by hand. Okay, it's a nice little pattern. Any questions on this one? It's kind of a basic one to do. All right, let's try one a little harder. Okay, so this one is 2x plus y to the fourth. All right, so this time, you got to be careful because we have this 2. All right, so as we do it out, this is basically like my a, this whole thing. Okay, and then b, well, that's what's right there. All right, so as you fill it in, a is a little bit more complicated than just a single letter. Okay, it's got a coefficient. Anytime you use a, put it in parentheses, because it has 2 and x. Keep those grouped together. Okay, you'll see why in a second. Right, so your first term is going to be 2x to the fourth. Okay, and the coefficient there is a 1. Any question on that? Okay, who give me my next term? What do you think the next one will be? Josh?
4, 2x to the third.
Yep.
B, or y.
Y. Yeah, I just put A and B up there because those are the letters I used before. So if you're trying to match it up with what we did, that would be your second term. There's a lot more we have to do out here, but let's just try to write the terms first. Yep.
Is it in the first set of terms? Shouldn't there be y?
In this one?
Yeah.
No Y in the first one.
Oh, right, sorry.
If you want to think of it as y to the 0
Yeah,
power,
yeah.
you could think of it that way. Just like in the last term, there won't be a 2x. Okay, how about Orlando? What's my next term?
6.
Yep.
And then 2x squared
Good. 2x squared,
times y to the second.
y to the second. Good. Okay, now we're going to do our, we've hit kind of the middle of that triangle. The coefficients are going to start going back down. So we get 4 times 2x y cubed. And the last term is going to be 1. And now 2x is gone. It would be 2x to the 0 power, y to the 4th. Okay, now, in something like that, we gotta clean it up a little bit. Okay, remember, when you have a product raised to a power, okay, raise each factor to the power. Okay, so let's start with 2 to the 4th. Sylvia, what's 2 to the 4th?
2 to the 4th. 64.
2 times 2 times 2 times 2. 16. We're not done yet. I got a hard one for you. Times 1.
Times 1. Is that 16?
16. And now, also don't forget we have to raise x to the 4th power. Okay, once you do this out, you lose the pattern in Pascal's triangle. Okay, but we do have to do out all these powers and see what we get. Okay, Justin, what about 2 cubed times 4? 32. X cubed y. Any questions so far? Okay, anyone think they can give me my next term? Do everything you can out. Yeah?
24x squared y squared.
Good. 24x squared y squared. 2 squared is 4. 4 times 6 is 24. X squared y squared. Okay, next one. There's no power to do out on the 2x this time, so it's just 4 times 2 is 8xy cubed. And then the last one, there's nothing to do out. Just write it as y to the 4th. Questions on that? Okay, again, notice once you do it out, those coefficients, you don't have that nice symmetry anymore. Okay, like the 1, 4, 6, 4, 1, they change a little bit. Okay, what would be a little bit more challenging would be if I gave you something like this and asked you to go backwards and say, how would you get this? Okay, that could be tricky to figure out. There's patterns you could look for. I mean, you know it's to a 4th power because all your exponents add up to 4, so we should have that. Okay? But the x and the y, it'd be a little tricky to figure out exactly what it could be. But you could do it. Okay, you could do it. All right, this one's a little different because it has a negative. Okay, our binomial theorem doesn't really cover what to do when you have a negative there. So what could I do so I don't have a negative there? I can't just get rid of it, but I can kind of rewrite it a little bit. Yep.
You could do 3x plus the negative 2y, and then raise it all to the 3rd power.
Yeah, raise all that to the 3rd power. Okay, so now this is like your A, and this is like your B. Before we start doing it out, any guesses what's going to happen when we do out the final answer because of this negative? What do you think is going to happen with the terms now? Yep.
It's going to be subtraction instead of addition.
All subtraction?
So.
Some subtraction? Yeah?
Some of the terms might cancel out.
Okay, so you got a positive, yeah, you might have some cancel out. All right, so well, let's do it out and see what happens. Okay. But be careful with that negative. Okay, that is going to change a little bit from the pattern we've seen. Okay, so Carly, what's my first term going to be?
27x cubed.
Yeah, and you know what I'm going to do just to start out? Because we're going to get into a lot of calculations we have to do. This one is pretty easy to do in your head, and you were fine. But I'm just going to write it like that for now. Okay, so 3x cubed. Okay, how about the y term? Do we see it yet? No. Okay, and I'm going to put the coefficient so we can see where that comes from. Okay, what's my next coefficient? Okay, 3. Okay, we're going down in the 4th row. So make sure you start with row, 3rd row. Start with row 0. So 3 times, Shannon, what's going to come next?
3x. And then negative 2y.
Anything before the y?
Yeah.
Yeah.
Put a square.
Yeah, so it's going to be 3x squared and then a negative 2y. So there's all kinds of things we gotta do out here. Okay, plus. How about Lasan? What's my next coefficient? 3. Good. Okay, and Nick, what's going to go in the parentheses here? First step.
3x.
3x. And how about the second parentheses?
Negative 2y and then squared.
Good. Negative 2y squared. Okay, and the last part, coefficient's going to be 1. The 3x, that term, that's gone. And you just have negative 2y cubed. So now if you kind of look at what's going to happen, every other term is going to be positive, negative. Right? That's what will end up happening. So some of the terms will be negative, exactly half of them. Right? So the first one Carly already gave us, 27 x cubed. Okay. Anyone think they can give me that second term, doing out all that arithmetic? Brian?
27x squared minus 6y.
So once we combine it, there should only be one number. One single number. So I see where you get the 27, so that's good. But you can multiply that by negative 2.
How do you want to do it?
Yeah.
Negative 54.
Good. Negative 54xy. Okay, and make sure it's x squared. All right, so 3 squared is 9 times 3 is 27 times negative 2 is negative 54 x squared y. All right, let's try the next one. How about Tahina? What would I get for the next one?
$36xy squared.
Perfect. 36xy squared. Good. Okay, last term, this one's pretty straightforward. Negative 2 cubed is negative 8, y cubed. Okay, so binomial theorem using Pascal's triangle. Quick way to do out any binomial to a power. Any questions on those? All right. This one, I'm going to hold off on. Does anyone have a question how you do this one? The only thing that would end up happening here is you'd have a power to a power. Okay. What happens when you raise a power to a power? Yeah?
You multiply the two exponents?
Right, you end up multiplying the exponents. Okay? So this would be your first term. This would be your second term. And anywhere that you have a power to a power, you'd end up multiplying the exponents. But I actually think this one is easier than that one because you don't have to worry about a negative here. Right. So any questions on how you do something like that? Question, Sylvia?
Oh, I was just asking, so if you would go to the 6th row, this
Nope, third row. Because that's the power we're raising to.
Oh, okay.
Power you're raising to is whatever this exponent is on the outside. Yep. So you'd be using the coefficients 1, 3, 3, 1 again here. All right, so if that exponent is small, Pascal's triangle is pretty easy to use. But if n starts to get really big, okay, we need a better way to do this out. Not that it's hard to do Pascal's triangle to the 20th row, but first of all, you could make a mistake, and it's going to waste a lot of time. Okay, the other part is easy. Okay, if you had something to the 20th power, and you had an x and a y, it's just going to start out with this pattern. And just keep going. Just have your x's go down by 1, have your y's go up by 1. This is the hard part. Where are we going to get these numbers that are supposed to be in front from, if we're not going to use Pascal's triangle? Okay, and that's where factorials come in. Okay, so first thing is we'll just make sure everyone remembers what that is. Okay, so with factorial, okay, they use this symbol, n, with an exclamation point. Okay, so you pronounce it n. Okay, that's how you say it. Okay, so n is 1 times 2 times 3 times 4. You multiply every number up to n. No exclamation point there, just n. All right, so it's a product of every integer from that number down to 1. So like 5 factorial. 5 factorial would be 5 times 4 times 3 times 2 times 1. Okay, factorials get very, very big very quickly. Okay, they grow even faster than like an exponential function. Like if you took a number and tripled it each time, that's nothing compared to a factorial. All right, so let's try doing out a couple factorials, and then we'll talk about 0 factorial, because that's a little weird. Okay, what do you think 1 factorial is? 1. It's the product of all the integers from that number down to 1. Well, it's basically itself. How about 2 factorial? 2. It's the product of all the numbers from 2 down to 1. How about 3 factorial? Yep, it's the product of all the integers from 3 down to 1. And then 4 factorial?
24.
Yep, 24. It's 4 times 3 times 2 times 1. And how about 5 factorial? Yeah, 120. So very quickly, by the time you let your number get to 5, you're already in the hundreds. Okay, so it grows very quick. How about 0 factorial? This one's kind of weird, and this is going to be more of a definition. Carly, did you have a guess?
I was going to say 0. Maybe.
0? Well, let's look at the pattern. Maybe we can figure out a pattern. What can you do to 24 to change it into 6 using division? Divide by 8?
4.
Now let's try 4. So divide by 4. How would you change 6 into 2? Divide by 3. 2 into 1? Divide by 2? Divide by 1.
So is it 1?
It's 1. Okay? And it looks a little strange, but it does follow the pattern. Divide by 4, divide by 3, divide by 2, divide by 1. Okay, so 0 factorial is 1. Okay, on your calculator, the button for factorial, I'll just show you where it is. Type in 5. It's under math, number. And hold on. Is it under number? No, it's under probability, I'm sorry. Under probability, it's the 4th option. Okay, now you can do decimals. Okay, like you could type in 5.5 and do a factorial. Okay, and it'll give you an answer. When you start doing decimals with factorial, it's a little complicated. In fact, you can only do some decimals on the calculator. The calculator, I think, will do anything that are 0.5s, but they won't do anything else. You can extend factorial to real numbers. Okay? We're just using it with integers. All right? When you extend it to real numbers, it involves pi, and it gets kind of weird. It's not something we're going to need. Okay? I just want you to know it can be done, but don't worry about doing it for this class. Does anyone have any questions on just doing factorials with integers? Okay? Domain is just our integers. Okay, so another thing when we start to get into probability is to be able to do something, let's say, let's go even bigger. Something like this divided by something like this. Well, some of these numbers are getting big enough that you can't even plug them in on the calculator. I think somewhere around 60. If you try to find 60 factorial, it's too big. No, that one still fits. Once this exponent goes over 99, I think some of the older calculators, they're gonna stop doing it. That's a big number. It's pretty big. Okay. What does 15 factorial really mean? It means to do what?
Basically means 1 times 2 times 3, multiply all the way up to 15.
Right. Okay, so if you had 15 times 14 times 13 times 12, all the way down to 1. And then in the denominator, you had 12 times 11 times 10, all the way down to 1. There's a lot that cancels out here. Okay? All of this basically cancels out. And all you have to worry about doing is this pretty relatively small calculation. 15 times 14 times 13. Okay? So when we start to do factorials, we're going to try to reduce what we can first, so we don't have to plug in things that are either impossible to plug in or really, really huge. All right? All right, so we can use the idea of factorials to find our coefficients, okay, instead of Pascal's triangle. Okay, so suppose you want to find the number that's in row n, column r. Okay, so we're going to go row n, column r. So for example, in the triangle, if you wanted row 3, column 2, you go down, that's row 0, row 1, row 2, that's row 3, column 0, column 1, column 2. Okay, so we always start with the 0th row, 0th column. That's 3 is the number in row 3, column 2. Okay, and the notation we'll use is that. Okay, so if you wanted to know the number in row 3, column 2, you'd write this. And the way you pronounce it is 3 choose 2. And the reason we pronounce it this way is because it has to do with combinatorics. Or if I said to you, I have 3 markers, and I want you to pick 2 of them, how many different ways can you do it? Well, you could pick the green and the red, you could pick the green and the black, or the red and the black. There's exactly 3 ways to take these objects and pick 2 of them at a time. There's 3 ways to do it. All right, we'll tie in that idea a little bit more next week. Okay? I just want you to understand where this pronunciation is coming from. So like if it's 5 choose 2, that means if you had 5 different objects, how many different ways can you pick 2 out of the 5? Well, in Pascal's triangle, if you go to the 5th row, column 2, it would tell you how many ways there are to do that. Okay, just make sure you always start with row 0, column 0. All right, so this gives us a notation for what we're looking for, but I still haven't explained if I said, okay, I want you to tell me row 10, column 4, what's the number in that row? Well, still need a formula to do that. Okay, we could go through the proof, but I'm going to hold off on the proof. That's the formula. Okay. So here's the formula to calculate the number in the nth row, r column. Okay, row n, column r. Take n factorial, divide by n minus r factorial, then multiply by r factorial. So there's a lot of canceling that's going to happen here. Also, every time you do this, you should never get a decimal. Okay? You're always going to end up with integers, because that's how Pascal's triangle works. You're adding integers above it to get the integers below. Right, so here's how you could write Pascal's triangle in our new notation. Okay? This is row 0, column 0. Okay? The next one is row 1, column 0, row 1, column 1. This is row 2, column 0, row 2, column 1, row 2, column 2. Row 3, column 0, row 3, column 1, row 3, column 2, row 3, column 3. And if you plug these numbers in exactly, let the top one be n, the bottom one be r. If you plug them into that formula up above, you'll get exactly Pascal's triangle. Okay, so you just have to follow that formula. A little time consuming, but certainly not as bad as if you had to generate the 15th row by hand. Now you've got a formula. You could even write a program on the calculator. You just type in n, you type in r, and it does all that work for you. Let's type in those two things. Okay, this is on, it's in your book on page 605. Okay, does everyone understand what you call the columns and rows, how you number them? Start at 0, 0. Okay, so now it looks kind of confusing, but if you look at it, it's just our binomial theorem rewritten with our new notation. So your exponents on A are always going down by 1 till they finally disappear. Exponents on B go up by 1 till they finally reach the highest exponent that you started with. And then the coefficients, well, if you want to raise it to the nth power, you're always going to be in the nth row, and then start with the 0th column, then go to the first column, the second column, third, fourth, fifth column, till finally you get to the last column, the last in that row. So I think that notation looks kind of confusing, but it's actually not that hard to just do an example. Okay, let's just try to find a couple binomial coefficients. Okay, so the first one is 6 choose 4. Okay, let's just make sure we know what n and r come out to. Okay, Lisan, what's n in this case? 6 and r? 4. Now just fill into this formula. N factorial, divide by n minus r factorial, times r factorial. All right, n factorial divided by n minus r, that's 2 factorial, times r factorial. And that entire denominator should cancel out with what's in the numerator. If it doesn't, you're going to get a decimal. Okay, so everything in the bottom should disappear. To see it, let's just write it out. So in the top, 6 times 5 times 4 times 3 times 2 times 1. You don't have to write the times 1. In the bottom, we have 2 factorial times 4 factorial. Okay, anybody see what I can cancel out? I think there's a big chunk of stuff we can cancel out all at once.
4, 3, 2.
Yep, 4, 3, 2. And the 2, it's got to go into something. I said there's no decimals. What does the 2 go into in the top?
The 6.
Yeah, the 6. So now we've got a calculation we can probably just do in our head. This is all gone. So we have 3 times 5. That's it. Versus if you tried to deal with 6 factorial in your head, that's pretty big. But you don't need to, okay, because it cancels out. And I think we even did out the 6th row earlier in one of our problems. If you go back and check, there should be a 15 in the 4th column. All right, let's try. This is one we haven't done out. I'm going to go all the way to the 9th row, 5th column. Can anybody just set up my my formula, plugging in n and r. Yeah, go ahead, Josh.
9 factorial over 4 factorial times 5 factorial.
Yep. So n factorial over n minus r, 9 minus 5 is 4, times r factorial. Now, after a while, you don't even need to write this out the long way. You can kind of figure out what's going to cancel in your head. Like, I know if I have a 9 factorial and a 5 factorial, everything from 5 down is gone. Okay, I can do that right away. So I have 9 times 8 times 7 times 6. I don't need to write 5, 4, 3, 2. That's going to cancel with the 5, 4, 3, 2 right here. Okay. Okay, now everything there should reduce, and you can do it any way you want. Doesn't matter how you do it. Do 4 into 8, do 3 into 6, and then do 2 into 2. So in the top, you're left with 9 times 1 times 7 times 2. All right, so 9 times 1 is 9. 9 times 7 is 63. 63 doubled is 126. Anyone else get 126? 126, good. Okay, so any question on that? So a couple of those on the test. Just calculate a binomial coefficient. Okay, and then last two types of problems. These problems are really just keeping track of where you're at. Okay, all I want to know here is what the 12th term of this expression would be. Okay, you don't have to tell me the whole thing. Just the 12th term. Well, the first thing we should probably start out is we're going to need the coefficient. So what row in Pascal's triangle would I be using here to raise something to the 15th power?
15.
Row 15. Okay, so I need that. Okay, what column? If I want the 12th term, I'd be in the 12th column. Okay? So to find the coefficient, for your row, look at your power. For your column, look at the term you want. Any questions so far? Okay, now the next part. You're going to have a 2x raised to some power times a 3y raised to some power. We just have to figure out what those powers are. You know, like is it, they got to add up to 15. Okay, so you want the 12th term. So what do you think the power is going to be? Yeah?
For x it'll be 3, for y it'll be 12.
Yeah. Okay. Another way to do it, you could write it out if you had to. You know, just leave like some spaces. So I know if I FOIL this out, I'm going to have 15 terms. Okay. I'm looking for the 12th term. So that's the one I'm looking for. Okay. And then you could kind of count through and see what you got. This would be y to the 0, wouldn't exist. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count right? Yeah, what you said is correct, Cassie. Oh, I know what I did. Remember, whenever we're using Pascal's triangle, we always count them starting with the 0th term. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? You got to start with the 0th. If you don't, it messes you up. So this is your y to the 0, y to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's your y to the 12th. Okay? This would be your x to the 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. 3. Okay. Just remember when you count, start with 0th term in this kind of problem, because that's how Pascal's triangle works. Okay. All right, let's do this part out. This part's pretty quick. 8x cubed. Let's see, wow, they actually did that out. That's going to be pretty big. Okay, 3 to the 12th. I'm going to hold off on doing it out. It's going to be, it ends up to be about 1.9 billion. Okay, so just leave it. 1.9 billion x cubed y to the 12th. And now let's do this out. Let's just do it down here. So n factorial over 3 factorial, 12 factorial. Okay, on 15 factorial, what's the biggest thing I can cancel out? Everything from what number down? Yep. Everything from 12 down is gone. This time. Okay? And in the denominator, you're going to have 3 times 2 times 1. Or you know what? You could put 6, but I think it's easier to reduce if you leave it separate. 2 goes into 14, 7. 3 goes into 15, 5. Okay, so my coefficient is going to be 5 times 7 times 13. 455. And then when you multiply the rest out, it comes out to like 1.9 billion. Any question on that? Okay, let's take the same problem. Let me show you one other way it could be worded on the test. Instead of saying finding the 12th term, it could say find the coefficient of the, I don't know, let's say x to the 7th, y to the 8th term. Okay, in fact, I'll make it even simpler. Okay, so let's look at x plus y to the 15th. Okay, so I took off the 2, I took off the 3, I'm just making it simpler. So in this binomial, x plus y to the 15th, find the coefficient of this term. Okay, how would you do that? How would you figure out what row and column you're looking for? One of those, I think, is very, very quick to figure out. Yeah? Yeah, you're definitely in row 15. Just add your exponents. Okay, now the column is the term number, starting with the 0th term. Okay, so one way to do it, if you're going to have 15 terms, start at the 0th term, okay, and look at where x to the 7th would come up. Okay. Well, the first one would be x to the 15, 14, 13, 12, 11, 10, 9, 8, 7. That's where your x to the 7th, y to the 8th term would be. Okay. Now, counting from the 0th term, what term is that? 0, 1, 2, 3, 4, 5, 6, 7, 8. That's the answer I'm looking for. In Pascal's triangle, I want to know the number of 15th row, 8th column. Okay. It also just happens to be this number right here, but there's several ways you can reason that out. Notice the same. Okay. Any questions on that? Any problems with doing this out? Everyone thinks they could do this out fine? Okay, it'd probably be pretty big, but if I ask you for a number, I'm going to try to make it manageable so it's not in the billions. Okay? All right. All right, so the homework okay, tonight is on page 606. And it's 1, 3 through 8, 11 to 15, 17 through 19, and 21 through 25. Okay, so we'll take a look at that tomorrow, and then we'll have our test on everything in chapter 11 so far.